In the last video, or the intro video, we talked about the variables that are used to describe the gas. And just to review some of the list, we got pressure, volume, temperature, and amount. And we're going to talk about how we determined what the relationship between these variables are. And usually we found them out pairwise. So the relationship between pressure and volume for a gas was first put forth by Robert Boyle. And what he found is that, so in the system here, this is called an open manometer. And so there is gas in here, and this is liquid mercury, and it traps the gas in there. And if you do this, what will happen is that the mercury level initially, you'll see here, is equal on both sides. So what happens if you add more mercury? And in this case, to the point of another 760 millimeters. So the weight of that mercury is bearing down on this trapped gas here. Now this is a very important height of mercury. This is the amount of mercury whose weight at sea level corresponds to the weight of the entire atmosphere on you at sea level. So now we've got the actual atmosphere and this additional atmosphere's weight worth of mercury. So this now has 2 atmospheres of pressure is acting on this gas. And what you find is that we doubled the pressure and the volume went down by a factor of 2. And found that, and that this was a fairly quantifiable relationship, that the volume got smaller as the pressure was increased. And if you plotted it out, you always got something like this. So it went down. So this is called an inverse relationship. So that when the pressure is high, the volume is small. And when the pressure is low, the volume is larger. So again, this is mathematically, this is called an inverse relationship. And what you find in cases like this is that, basically the idea is that one goes up, the other one has to go down. And that for relationships like this particular curve, their product is a constant. Remember that when you're doing your lab activity. Next is the relation between temperature and volume. So what people have found, so we have here is a trapped sample of gas with this mercury plug on top of it, and atmospheric pressure, at this open end of this tube. So what this means is that because this end is opened, the pressure inside here will always be constant. And that if the volume can change because this mercury plug isn't fixed, it can move up and down. And what people found is as they changed the temperature, namely as they heated it, the volume of the gas got larger. And they found that it was, at constant pressure and amount, that there was a linear relationship between these. Then again, if you doubled the temperature, the volume doubled. If you reduced the temperature by a factor of 2, the volume was reduced by a factor of 2. Now, it is important to note that this is actually how the absolute temperature scale was determined. That, as you cool this thing down, the volume is getting smaller and smaller, and people thought to themselves, well, what if we just continued this straight line all the way down to where the volume is in fact 0? And we will call that the lowest possible temperature, because nothing can have a volume less than 0. And this was the beginnings of the absolute temperature scale. The definition is a little different in modern times, but the idea is the same. And that corresponds to negative 273.15 degrees Celsius. So in the absolute temperature scale, kelvins, this is 0. And it's important that in any gas calculation that you're going to be working with, the temperature absolutely must be in kelvins. So remember that. Now the person that figured it out was a Frenchman by the name of Jacques Charles. And he found that the gas tend to get smaller when you cool them, and found that if you quantified it, the volume was directly proportional to temperature. And so in equation speak, volume is equal to some constant times temperature. Or that for any gas sample of constant pressure and amount, the ratio or the quotient of volume and temperature is constant. Keep that in mind for the lab activity. The relationship between the amount of a gas, number of moles, and its volume was figured out by Joseph Gay-Lussac. He was an avid balloonist, which is how we got into the relationship between gases and their various state variables, and studied their properties a lot. And he also had discovered in the course of these studies this thing called the law of combining volumes. Now in English, that said that at a given temperature and pressure, the volumes of gases that react with one another are in the ratios of small whole numbers. So what this meant is that, so the experimental observation was that 2 volumes of hydrogen would react with 1 volume of oxygen to form 2 volumes of water vapor. And an Italian scientist by the name of Amedeo Avogadro, of number fame, had proposed actually a molecular level interpretation of that, namely that 2 volumes of hydrogen, there are 2 hydrogen molecules, reacted with 1 oxygen molecule to form 2 molecules of water vapor. And what Avogadro had said that, tie those 2 together and proposed that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules, or equal number of moles of molecules. These operations were summed up in what is now called Avogadro's law, that said that volume is directly proportional to amount. In colloquial English, more stuff, more space. Now, in equation form, we would say V is proportional to N. In graph form, it looks like this. So as you increase the number of moles of gas, the volume it occupies increases linearly. And so again, if you double the amount, the volume doubles as well. If you triple the amount, the volume triples.